Hey guys, how's it going? Long time no see. I am back with a video about a foundational topic I just published on. I'm going to try and make the video as accessible as possible. It's going to touch on cool things like quantum chaos, random matrix theory, and studying late time properties of quantum systems. So without further ado, let's jump into the video. So when you study quantum dynamics in a condensed matter type system or some finite level system, you often come across really big summations where every term in the sum looks like the following expression. So here I'm going to take the energy eigenvalues out of some Hamiltonian in the usual way, and we're going to try and keep our discussion really general. Here Z is going to be some complex number that's going to depend on the type of quantity that we're studying. As a complete side note for the more advanced crowd, I'm going to assume that the only symmetry in the Hamiltonian is the Hamiltonian itself. So the presence of other symmetries usually causes degeneracies. And for topics like the one we're going to talk about today, we need to resolve all of those symmetries before starting our discussion to get an accurate picture of the energy spectrum properties. So back to the dynamics, one could, for example, write down the expectation value for some observable in time, evolving according to the Hamiltonian, and the expectation value will be taken to be with respect to some pure state, and we would get the following summation. The expectation value falls into the class of functions that sum over terms like our general example. But because I want this conversation to be as general as possible, we won't stick with this example. Instead, let's return to what a single term in the sum would be. We oftentimes want to talk about late time properties or infinite time properties of dynamical functions. And if those late time properties exist, or if late time or equilibrium is well defined, then to study them, what you can do is you can take the equilibrium value to be the infinite time average of your sum. And the way this analysis sort of works out is you can take the infinite time average of every single term. So how do we evaluate this expression? We really only need to understand the energy differences here to understand which terms survive the infinite time average. So basically what happens here is that if the difference is 0, the expression is a constant, and the average of a constant is a constant. And if the difference is non-zero, then what's going to happen is you have a complex number that's going to be rotating around the complex plane indefinitely. So its average value will be 0 as it's oscillating around 0. So in general, if our model doesn't have a degenerate spectrum or a spectrum of energies that don't repeat themselves, this means that the dynamical terms that survive this type of averaging are the ones with equal indices or equal energies. So when would we expect not to find degeneracies? A good example would be quantum chaotic models. So let's say our spectrum is ordered, or we write the indices in such a way that it's ordered so that EM is less than EM plus 1. We can define the level spacing then as SM is equal to EM plus 1 minus EM. And basically in these types of models, these quantum chaotic models, we have a level spacing distribution that has level repulsion. And this is given here by this expression for the probability on the spacing or the level spacing of the distribution. So the level repulsion here is given specifically by the linear term in front of the exponential. So the probability directly at 0 is 0, but this is of course a probability density function. This distribution is called the Wigner surmise, and studying this distribution when you're studying the properties of the spectrum it's a super common probe for quantum chaos or chaos in quantum systems. There's a really interesting history behind this, and maybe I'll do a video on this in the future. But the intuition that I want you to draw from here specifically is that the probability of the level spacing being 0 is exactly 0, and it only grows linearly for small gaps. And so this property is specifically, again, called level repulsion in the gaps of the energies, and it might give us confidence to say that we don't expect there to be degeneracies in the spectrum, or we don't expect degeneracies to be common in the spectrum. So we could consider, for example, more complicated dynamical terms that include not 2, but they actually include 4 energy quantities in the exponential. So this is a much more complicated quantity, and we find physical motivation for it, for example, in the case of out-of-time ordered correlators, which are a standard probe for quantum scrambling. Quantum scrambling being, a probe for quantum chaos, or maybe it's not actually a probe for quantum chaos. We think there's no clear connection yet, in my opinion. I haven't seen it. Maybe for the late time properties, but certainly not before. But that's sort of a side story that we could talk about at a later time. So again, finding the late time properties of expressions like this for these types of systems, it's the same problem as before. You want the exponential, the argument of the exponential to be 0. So a term that survives the infinite time average would be a term where em plus en minus ek minus el is 0. So when could this expression be 0? Well, there's always going to be solutions, because we could pick, m is equal to k and n is equal to l, or swapping that, m is equal to l or n is equal to k. So there are solutions, but at face value, one might actually expect that this would also give you solutions of 0 when all of the indices are not equal, so a generic set of indices. Now, this gets to the topic of the video. If a solution to this equation is valid and it doesn't fall into this trivial matching of indices that we just did, we call it a resonance. And we are going to assign an order to that resonance. The resonance that we might have just described there would be a Q is equal to 2 resonance, as I call them. And this is because there are 2 energies adding and then 2 energies subtracting. And so a degeneracy in the spectrum itself would be called a Q is equal to 1 resonance. The presence of resonances is unfortunately very inconvenient for analytics. It creates, sort of difficult bookkeeping while you're trying to prove things. And of course, resonance are very model dependent. It depends on the system that you're studying. So a typical hand wavy way that hand waves away the Q resonances is that the models that are chaotic shouldn't have resonances at any order. One can also provide sort of random matrix theory type arguments where models with resonances or Q order resonances for arbitrary Q are vanishingly rare. Unfortunately, the models that we care about are just picked out of a hat, right? Like we study the matrices and the spectrums that we study for a reason. So they might have resonances, and they might just be these rare matrices that you can rule out with random matrix theory. And surprisingly, up until now, there hasn't been any evidence that that chaos prevents Q order resonances. So the fact that there's no evidence for this doesn't stop us from asking a very interesting question, and that is, are there general properties one can find if there are no resonances at any order for the system? And the answer to that is yes, you can find extremely powerful results. In particular, we can provide a really, really strong lower bound on the quantum recurrence time. Quantum recurrence time is the time it takes for a system to return close to its initial conditions. If we take a condition that we'll call the Q no resonance condition to be true, meaning we don't have resonances at any order, the quantum recurrence time for, say, the fidelity or the expectation values of observable in time, this can be lower bounded by something that goes like e to the volume of the system, where c is some constant that makes the expression work for the for the result of the paper. So a small assumption here that seems to be generally true for chaotic systems is that exponentially many energy eigenstates are going to participate in the dynamics with meaningful weight. So if you are curious about this result, you can check out my video on the concentration of equilibration, or my article. I'll put that article in the description. So assuming that our model has no resonances at any order is actually an extremely powerful analytical technique, and it gives you, recurrence times that are extremely large. So the real question here is this assumption actually warranted? And so to test this, we're going to do some numerics and investigate if chaotic models should satisfy the Q no resonance condition. So a key thing to understand for spectral statistics is if we're not going to get the Wigner surmise and we're not going to get level repulsion, what else should we get? And the answer to that is usually what we find for integrable models, for example, is that the level spacing is Poisson. So the spectrum behaves like independent random variables, and instead of level repulsion, we get level attraction. The spectrum or the gaps in the spectrum cluster around 0. So how should we go about studying this numerically? Well, I think this solution is obvious given what I've said. What we're going to do is we're going to study spectral statistics of a specific chaotic model, and we're going to try and apply spectral statistics to a spectrum that resembles our Q is equal to 2 or greater case. So we need to define a new spectrum. So for the purpose of the video, though, we're only going to talk about the Q is equal to 2 case. And actually, all of the Q is greater than 1 cases behave qualitatively similarly. So there's really no point to talk about anything but the Q is equal to 1 and Q is equal to 2 case. So we can construct our new spectrum by constructing the following quantity. So we have lambda KL is equal to EK plus EL. Now, right away, you should spot an obvious symmetry in this spectrum, and we need to resolve that symmetry before moving on. So the spectrum is invariant under swaps of the indices. So lambda KL is equal to lambda LK. So we only want to work with the portion of the spectrum where L is greater than K, for example, and this resolves that symmetry. And we're also going to remove the K is equal to L portion of the spectrum, but that actually shouldn't affect the results because that's just a linear portion in the dimension compared to, a quadratic portion when we combine the two spectrums. Now, I don't want to complicate things too much, but the level spacing distributions really aren't the best probes for quantum chaos. So what we're going to do is we're going to use a different spectral test, which I'll introduce right now, that's a little bit more robust and a little bit more modern. And we're going to call this the ratio distribution. So what we're going to do is we're going to take our spectrum lambda KL, and we are going to assign it for each KL, we will give it an integer index alpha, and we will assume that integer indexing orders the spectrum. Then the gaps in the spectrum of this new spectrum are given by the following equation. Then the ratios that we're going to study the distribution of are given by the following expression. So Rj is equal to the minimum of Sj plus 1 divided by the maximum of Sj plus 1. So it's just going to be the smaller one divided by the bigger one. And so this tells us that Rj is in between 0 and 1. So if the model is quantum chaotic, we have a prediction for that. What we get is this probability density function, so 27 over 4 multiplied into these two polynomials. And if it's Poisson or experiences level attraction, then the distribution will look like the following distribution. And so this is going to be our smoking gun for the video. In the article, which I'll link below, we did more tests. So you, for example, can maybe get a bit more fancy and calculate the expectation value of the ratios and see how it converges precisely to the predictions of these distributions. But I just find that, just plotting these distributions and then plotting the data is just more visually appealing. But if you want to see deeper analysis, please check out the article. So to study this, I checked a typical quantum chaotic model. The content of the model, isn't super important. We actually also studied this for random matrix models that have Wigner-Dyson statistics, the Gaussian ensembles of random matrix theory. And it doesn't really matter. So the result that I'm about to show you seems to be generic. It's true for random matrix theory, the Gaussian orthogonal ensemble, the Gaussian unitary ensemble, and it also seems to be a generic observation for quantum chaotic models. They agree. But first, as sort of a warm-up, let's check the Q is equal to 1 case to demonstrate the model that I'm investigating is in fact quantum chaotic. Let's look at this plot. In black, what we have is the quantum chaotic prediction or the random matrix theory prediction. And in maroon, we have Poisson. And so the spectral statistics of this model for Q is equal to 1 agree with the predictions of random matrix theory. Okay, so let's move up 1 and go to Q is equal to 2 and study this new spectrum. We get Poisson statistics. So for the higher order spectrum, we get level attraction rather than level repulsion, which means, unfortunately, maybe the no resonance condition isn't as safe as it's been previously assumed to be in the literature. So finding this result doesn't necessarily tell you that there are violations. It is a continuous distribution, of course, but it does tell you that the spectrum has a clustering property near zero gaps, right? Which means I wouldn't be surprised if there were violations or approximate violations. So an immediate interesting research direction then is to perhaps update work with this observation that assumed the no resonance conditions for all orders or some orders or something along these lines. So in the article that I performed this research in, we did this for some equilibration bounds, but that's not super important. And we of course also demonstrate this level attraction property for higher order Q. We only go up in the article to Q is equal to 4 for the chaotic physical model, the spin model, and we do up to Q is equal to 3 for the random matrix theory model. It does get sort of significantly harder every time you increase the value of Q. Okay, so is there an intuitive explanation for why we get Poisson statistics or level attraction? And the answer is yes. The spectrum you can actually think of as a non-interacting system for the Q is equal to 2 case. So you get the following equation. And in this equation, you can see 2 symmetries now that maybe weren't super obvious when I wrote down the spectrum of this model. So first is the invariance under reflection or translation or whatever you want to do to swap the 2 Hamiltonians from one Hilbert space to the other, which basically is how we swapped our indices previously. But most importantly, each individual H in this expression is itself a symmetry. It commutes with the total H2 Hamiltonian. And so the problem with resolving this symmetry, however, is that if you resolve it, you are no longer studying the physics you want to study, right? The late time properties of these higher order expressions require, a specific number of energy terms to be summed. And if you resolve this symmetry, this local symmetry of the Hamiltonian H and our H2 Hamiltonian, then what you end up with is you're back in the Q is equal to 1 case for that spectrum. So the problem inherently must have Poisson statistics. It must have level attraction because under the construction, you're always going to end up with a symmetry. So I've put the link to my article on the no resonance conditions in the description, and my article exploring the power of potentially having no violations, no resonances at any order. So check them out if you want to know more. But that's it for today. I hope you enjoyed the video. If you did, feel free to like, subscribe, and leave a comment below.